Okay, let's start. Any questions on the homework? I sent an explanatory note around on Piazza about the Peukert's expression, but any questions about that or any other aspect?
Link to upload the code.
Huh?
Link to upload the code.
Oh, link to upload the code. Yeah. Okay, good reminder. I have to set up on Dropbox. I'll do that. Yeah. Okay, so if no questions, I assume. There was one student asking me some questions just right now. So the intuition is the following, right? I mean, if there are two sources of non-ideality in this question. Number one, if you look at the processor power model, it is not proportional to frequency. So it's basically the processor is not energy proportional. So even if you're not doing any work, namely f equal to 0, the processor is still consuming some power beta. Okay, so that's one non-ideality because relative to something being the system being entirely energy proportional, and the other one is the battery. If k is greater than 1, then intuitively what is happening is that if I goes down, then an ideal battery, if I were to go down by factor of alpha, then T would have gone, the lifetime would have gone up by factor of alpha. But because k is greater than 1, so if I lower the current by some factor greater than 1, then the lifetime will increase more than that factor. Okay, so that's the effect of the nonlinearity. All of it translates into that if I had a totally energy proportional system, then by that I mean power was proportional to frequency, and I had an ideal battery, then changing frequency will not have any effect because I changed the frequency by a certain amount, the power consumed changes by the same factor, and because the battery is ideal in that case, so the available time will go up proportionately, and the amount of work done, which you can think of as the number of instructions that the processor can execute, will remain unchanged. These non-idealities lead to complications, but these are all straight kind of nice algebraic equations, so there will be, you can just differentiate and get the optimum, and if you are rusty on that, just use Wolfram alpha or one of these aids to do the symbolic derivative or do some plots to get the intuition. But intuitively, there would be some value more than f equal to 0, which would be the optimum. If you increase f a lot, then current goes up, and therefore the battery capacity, effective battery capacity, that is the time, is going to go down. Okay, so if you want to get a better feel of the Peukert's law, what it does, read the Wikipedia article. I think I've given the link there. It kind of gives alternative ways of thinking about that expression. So, okay. Anything? Okay, great. So last time around, I had gone through the synchronization, and we're going to begin to talk about that. If I look at the different sources of errors when it comes to synchronizing, then there are a whole bunch of things. Obviously, clock has an impact, so that's at each node, and we kind of discussed in the previous slide set a whole bunch of issues around it. But then when we are synchronizing, then essentially that's we have to somehow transfer time information from one node to another, and how often you do it is going to affect things as well, because if the clocks are drifting apart, then one way to maintain synchronization is to repeatedly synchronize, right? Repeatedly say what time it is, what time it is. But if the clocks are very drifty, then you have to resynchronize more often. Time of flight has an effect in this. So if, for example, let's say again, if we were setting our watches mutually, and if it were to take a long time for the message, what time is it, to get to the other party and back, then during that time itself the clocks can drift. So that can have an issue as well. computational latencies, they end up affecting things because you're trying to measure, we'll see that how much time it is taking when we are doing the synchronization, but because of interrupt latencies and software latencies, errors get introduced. So there are a whole bunch of these factors which come into play. And around these things, we'll see that there are many different ways one can think about how to go around doing time synchronization. GPS, NTP, IEEE 1588, and then kind of more custom schemes are variety of ways one could go around doing it. So let's look at some of these approaches. So first thing what we'll do is we are going to look at synchronization in a somewhat different sense, which at the very beginning of previous slide set I had talked about, which is we are not looking at synchronization in the sense of synchronizing in terms of a real number clock or some sort of a something that corresponds to our notion of time, but rather what we want to achieve is that the ordering should be correct. So I had this picture many slides ago where basically I have a bunch of nodes, each P1, P2, P3 represent the 3 network nodes, and they have some sort of a clock that they are supposed to maintain, and the property we want is that events which happen before, if event A happens before event B, then A should get a lower time value than B. So we just want to get the ordering right, and we don't care about whether the timestamp for E11 and timestamp of E12 correspond to our notion of time as measured by the international standards. So if the nodes were running independently, then timestamping would be straightforward. All we do is every time an event happens that we need to timestamp, then I just increment my counter. So I really don't need a physical oscillator in that case. All I do is increment the counter. And that would be entirely local. Some more complication kicks in now because there are message exchanges taking place, and so we can think of a causality between a causal relationship between two events. So like E11 is the message sent, and E22 is the corresponding message received, and therefore we also have to make sure that E22 gets a higher timestamp than E11 does, or like for example E12 gets a higher timestamp than E24. And that you can easily see will get violated if all we were doing was that independently at the nodes, every time event happened, we increment from the clock. Because let's say we started out all 3 clocks as 0, E11 would get 0, E12 will get 1 according to P1's clock, but meanwhile P2's clock would have incremented many times, so E24 would have received 3 according to P2's clock, but 3 is greater than 1 out here, and that kind of violates our requirement that overall across the whole system we want the timestamps to be consistent.
What happens to E32?
What happens to E32? We'll just increment. So let's say again, imagine P1, P2, P3 had these registers called clock, local registers. So E31 would have gotten the timestamp 0, E32 would have gotten the timestamp 1. So what that would mean is E32 and E12 in that model of independent clocks, they would have both received timestamp 1, and as would have E22. Okay. But that's obviously is violating our expectation that E22 should be more than E11, E12 should be more than E24, and so on and so forth. So we need some protocol which makes sure that there is a global notion of time, a global clock, which achieves that. Okay, so so that's what we would like to achieve, and in this case, simultaneity has kind of a meaning which may differ from what our wall clock might tell us, right? I mean, for purposes of this, for example, since E11, E21, E22, and E31 have no dependencies, we can say we don't care for all purposes; they are the same. So what we want if in your data structures class, you might have seen this concept of partial ordering. So we want to impose an order on these events such that if you were to think of that there is an edge from E21 to E22, E22 to E23, and so on and so forth, and then every time there is a message exchange, there is an edge, then I basically need to assign times such that anytime there is an edge from one node to another node, then the head node gets a lower time value than the tail node. Okay, so time in this case is just a number being assigned, and if these nodes had physically synchronized clocks, then life would be simple, because let's say P1, P2, P3 had clocks which were synchronized to GPS, then automatically all the necessary properties would have satisfied as long as the events were sufficiently far apart, right? So I mentioned that GPS gives us 1 PPS signal with a 50 nanosecond error. So worst case, what may happen is that you may have 50 nanosecond type errors between pairs of nodes. And so all you have to make sure is that if the events are separated by more than 50 nanosecond, then the simple strategy would be that just maintain 3 GPS clocks and timestamp according to them, and you'll always be fine. If events are closer apart, then things will again fall apart in that case. So this kind of stuff where you just need to get the sequencing right is often necessary and sufficient, right? I mean, for example, if a bunch of sensors and you want to know whether sensor A saw the thing before sensor B, because that tells you the direction of motion, for example. Or for example, in a database, 2 requests came in, which one came first, because that will decide in what order you modify the data. So we want to achieve that. So with physical clock, things are easier and arguably, but without physical clocks, what we want to make sure is that somehow we achieve the sequencing. So what we can think of is kind of some sort of a relation. So as shown in this right-going arrow on the events that we have in our system. So if A and B are events on the same node, then we say A happens before B. Okay, so think of this thing as happens before. Okay, if A is the sending of a message and B is the corresponding receive of the message, then also we can say A happens before B. That stands logical. And finally, if A happens before B and B happens before C, then by transitivity, A happens before C. So, and on the other hand, if we cannot say that A is happening before B, and that is, if both are true, A happens before B and B happens before A, then you can say they are concurrent. Okay. So in effect, what we want is some assignment which subject to these constraints work. So the idea now is the following, that every node has a local clock. So let's call it C sub I. Okay, and so each process, I guess, previous slides I was calling is P sub I. So N sub I and P sub I are the same. So every time an event happens at a node, it will consult its local clock and assign a number to it. Okay, so it will basically assign, if event A happens, then at processor I, then it will get the timestamp Ci of A. And then the overall network clock we can think of as some function C, whose job is the following, that if now I look at a net event B happening at any node, then C of B, that should basically be the same as Cj of B, right? I mean, all we do is we are assigning, if my clocks are synchronized, then assigning according to the local clock will work. So somehow what I need to make sure is that I'm updating this Ci at the different nodes so that this synchronization property holds true. But we are not measuring we are not making any claim in this case about the time following any sort of physical property. So if I were to take two events which by wall clock may be 10 seconds apart, but by this logical clock they will just have some number which satisfy these properties. So how can we achieve this? So what we want to make sure is that if A happens before B in this logical sense, then the network clock A should assign a timestamp to A which is less than the timestamp of B, which in turn means that whatever clock is there at the node where A happens and whatever clock is there at the node where B is happening, they should have this property true. So if A and B were happening at the same node, it would be straightforward. If A and B are happening at different nodes, then we need to just do some additional work for it. So it turns out if you kind of think about the properties we want, the answer is kind of relatively straightforward. So if A and B are nodes at the same, events at the same node, and if A happens before B, then all we want is that Ci of A should be less than Ci of B. And the other place where we have happens before is if A is the sending message by some node and B is the received by another node, then what we want to make sure is that A timestamped by the sending node has a timestamp which is smaller than B timestamped by the receiving node. So in this case, we have to make sure that the clocks at node I and node J satisfy this property. So to meet the first property, all we can do is to just increment every time an event happens at a node, we just increment the clock. Okay, so that will always result in C1 being satisfied. To meet C2, you can read it more, but intuitively what we have to do is whenever we receive a message, then have that message carry the timestamp from the sending node. So now I have the arriving message with a timestamp which is saying what is the clock at the time that message was sent at the sending node, and I also have a local clock, and I'll just do a maximum of the two, right? So if I have a receive event, then my clock will be updated to the maximum of my current clock plus 1 or the sender's clock plus 1. Okay, so I will just update to the maximum of 2, and that will always result in C2 being satisfied. So what this introduces is what's happening out here is that I have to carry clock information in the message, okay, so that parties can synchronize with each other. And in this case, since all we want is the logical ordering, then that's all. Just going to the maximum is going to always work. So so what this simple strategy basically lets us do is that every event in my network will now have a timestamp which satisfies the ordering that exists in the system. And like I said, in many cases you need this property, and so it's extremely useful, even though I cannot do things like measure speed and stuff like that. I cannot translate this time into physical time, but I can get logical consistency throughout.
Does this assume that the RTT is 0? Because if like there's an event just happening few milliseconds before and that sends a message to the...
Don't think in terms of milliseconds at all, right? So if a node is sending a message and another node is receiving it, then logically the sending happens before the receiving, even if it is 1 femtosecond before that. But
so what I mean is like the event misses it. So if there is like E11 and E21 and E22. So
what do you mean I misses it?
So like there's a if you can go to the image.
Okay.
So if like there's an event between E22 and E23.
There is nothing here.
If like what happens is if E2 for assumption if E24 sends a message.
E24 sends a message.
And E24 message is received by E3.
E24 is received by E33.
Huh.
Okay, so
So
if
must-
okay, so in this example, obviously E24 is being received by E12,
Hmm.
but if E24 is being received by and E33 is a corresponding receive event, then all we have to make sure is that E33 gets a global timestamp which is greater than E24.
E32 can be a lesser thing also.
E32 in that case could be greater than or less than E24, doesn't matter, but E32 has to be less than E33. So
Okay.
like for example, if E24 had a timestamp 10, let's say, okay, and E33 got a timestamp 15, then for E32, 11 is valid, 12 is valid, 9 is valid, they're all valid.
So that means it can be erroneous.
No, there's nothing erroneous.
Because if you're giving it 9, you're
Well,
globally.
but there is no constraint between these.
Okay.
Right? There is no it's strictly a logical constraint. So you cannot make, it doesn't really matter
Okay.
whether E32 according to your clock is before or after E24 because you can't say any causal relationship between them. Okay. So, so in this paradigm, all we care about is that if there exists a dependence, then the timestamps follow that order. If you cannot show a dependence, causal relationship between them, then it could be either way. So which is why, for example, E11, E21, they may have timestamp of any order, right? I mean, they could be the same timestamp. Okay. So that's the logical clock, and this, in a way, is one notion of so in you can think of time in kind of two different ways, right? One is time is basically telling us the ordering, okay? Something happens before something else. And this kind of runs into some observer dependence also. If I'm sure you have read about Einstein's experiments, thought experiments in relativity, where he kind of talks about moving observer and then how in the frame of the moving observer, the events could take a different order than a different one, right? So in many cases, so for example, if there is a computer and it receives let's imagine there is a sensor and it's trying to observe, I don't know, let's say it's trying to observe or hear two bomb blasts, okay? If we know nothing about the distance and all, then if it is purely hearing the two blasts, then the order in which it will hear will depend upon the distances to the two sources, right? I mean, if the nearby, if let's say blast A happens before blast B, but blast A happened at a farther distance, then the signal will arrive later, and therefore it will think that is later, right? So order can run into these complications, but what's happening out here is that every time a message is going, we are putting a clock in it, right? So it's as if when the bomb blast happens, the sound wave is carrying the local clock, so the sensor can see at what time the blast had happened according to that local clock. So what we are seeing out here are several things. Firstly, local clocks. B, that when messages are exchanged, there is time information carried in it. And then finally, we advance the local clock at a node, not simply as a function of the local clock, but we are also correcting it based upon information we are getting from the other nodes, okay? And that's how we maintain the correct global notion of time. Now, all of this is great, but like I said, it only gives us ordering, and ordering is sufficient for a class of applications. But then the examples I gave, right? Did event at sensor A happen before event at sensor B, or kind of the read request to a database come before write request, things like that. Okay, so like for example, one very common case is that companies like Google maintain databases in a distributed manner. So the same copy of the database is replicated at many data centers. And let's say I send it a write request, and that went to data center A. You sent it a read request, and that went to data center B. We have to make sure that the if my request came before, then the logical, the correct ordering is maintained. So database people, distributed database people worry about these kind of things quite a bit. And the other comment I made was that if I had clocks which were physically synchronized, that is, somehow they were synchronized in the sense of our wall clock through GPS, then we achieve this ordering automatically to the limit of the resolution and synchronization accuracy of my clock. So while this logical clock stuff is present in many protocols and all, where the sole purpose is to figure out did A happen before B at two different locations in the network, much of the attention goes towards getting clocks which are physically synchronized. And this is where probably the easiest way to do this thing is to use GPS. As we had mentioned earlier also, so the idea in GPS is that all the satellites have atomic clocks which are carefully synchronized from the ground, and you also take into account orbital mechanics and relativistic effects, because these are satellites moving pretty fast, and so all sort of relativistic effects have to be compensated for. But at the end of the day, in very simple terms, all that is happening is that a signal comes from a satellite, is received by the receiver. The signal carries the sending timestamp, and each satellite is doing that. And the primary goal of the GPS was to find location, but the way it finds, but for it to find the location, it needs to know the range between the receiver and the sending satellite. And if you have sufficient number of ranges to different satellites, then basically through simple geometry, you can find what is the best, what is the XYZ that explains that, right? So you kind of fit intuitively, you're trying to find the center of a, your best estimate of the center of a n-dimensional sphere. But the clock here at the receiver is not synchronized. We don't have an atomic clock out here. So the way the problem then is formulated is that instead of just estimating XYZ, we estimate XYZ and the time. Okay, so we formulate it into a four-dimensional problem instead of a three-dimensional problem, and therefore we need 4 satellites instead of 3 satellites, and at least 4. Okay, if you have more, then you can do a best estimate in that case. So essentially, if I know the time out here at which the signal arrived, then I can compute the range with speed of light being known. But in this case, we estimate the time here. Or more precisely, what we estimate is that by how much is the clock at this receiver offset from the atomic clocks. So we are really trying to estimate the offset delta. So which is the time at which the message was sent and the time at which the message was received, which is the little t, except that the little t is unknown because our local clock is not synchronized. So we measure that offset. So given sufficient number of satellites, we can solve this thing. And the nice thing out here is that the accuracy is pretty good. And as I mentioned in previous class, GPS receivers, not kind of the ones which are optimized for displaying location, but rather the ones which kind of expose the all the innards. They basically have a pin called PPS pin, where a digital pulse comes every second, and the edge of that pulse is guaranteed to be within a short offset from the actual atomic clock time. So pros of this thing is that I mean, there is a lot of effort which has gone into making that whole satellite infrastructure. It's very reliable. There are now Russian, European, Chinese, Indian, there are a whole bunch of other systems. So you can also have sort of additional redundancy in these systems. The challenge remains that it doesn't work indoors or under foliage or obstruction. So even like if you are in urban canyons or like in between E4 and Boulter Hall, it will take a long time for it to synchronize. If something goes bad, then correcting it can take time. It's also pretty energy hungry. Most GPS receivers are order of, let's say, at least hundreds of milliwatt. So keeping it up as your primary clock can be extremely expensive. So lots of challenges, and sometimes things go awry also. So in 2018, late 2018, there was an incident where they were upgrading the software on some satellites, and there was some error in that, and as a result, a very tiny microseconds type error crept in into the time estimate that the GPS receivers were making, and it only affected a region which was in Europe. So anything which was using GPS time basically went awry, and GPS time is used, excuse me. Yeah, GPS time is used in communication systems, by radio and television systems and all. So for example, in UK, some of the radio stations went offline, and so those kind of effects happen. So GPS, I mean, while it's a pretty reliable infrastructure, it's not perfect also. So so if you have a very critical system, you probably do want some backup there. So one thing which I've seen at conferences in this country that they talk about precisely against this possibility, I'm sure all of you have read about like EMP weapons, right? Those EMP blast, which will basically take out the satellites, and several countries are now experimenting with shooting down satellites and all. So the concern is that if GPS infrastructure is killed in a warfare kind of setting, then basically a lot of stuff we depend upon out here will bad things will happen basically. So so what's happening is here, and I'm pretty sure in other major powers, that they're using the plenty of fiber that exists terrestrially to essentially create a nationwide network for synchronizing clocks over the fiber. Okay, so while the default remains the GPS, but in case those kind of things happen, satellites are killed or whatever, then you will have this ground-based network for distributing time. Okay, one cautionary note that not all GPS receivers are designed for time. So if you look at many GPS receivers will say the time is something, right? They just show it on the display, or they send you over the serial port onto your computer, but they are not what you want, because you are not getting direct access to the PPS signal. Would anyone venture a guess that how much delay you see over a serial port or a USB, like a GPS receiver is sending you time is this, and your computer receives it? How much do you think by the time you get to see what's the latency, what's the variation?
1 second.
Huh?
Almost 1 second.
Nah, no, not 1 second. It's not that bad, but it's like order of 100 millisecond or so if you are unlucky, and highly variable. So you can't simply sort of use that as your source of time. So if you're communicating over serial or USB, but it's in tens or even 100 millisecond range, whereas what we are seeking is nanoseconds, right? So so one has to be careful there. There are also sort of other forms of glitches that come, and just the time to synchronize with the satellites. And also it's a great source when it works for you, if your system is suited for it. Like for example, in my lab in recent years, we have done a lot of work and all. You have seen my lab, it's in the basement. You can't get any GPS signal obviously, so we would run a long coax line to the outside and just to pick up the GPS signals. So indoors can be pretty challenging. If you have windows and all, and those are nice windows, as in not windows whose glass have a lot of metal content and all, then again you can get the GPS signal and perhaps pick things up. Okay, so that's GPS. The other one, other good source of time, and I'm sure in recent years, if you have gone, you may have seen these wristwatches or wall clocks and nightstand clocks which kind of claim atomic clock accuracy. So what's going on there? I mean, they don't have a GPS receiver. Those are very cheap clocks, so they're certainly not putting a GPS receiver there, and they're sitting inside your home. So there is another time distribution service that exists. Again, I'm talking in terms of what's happening in the US, but there are similar things elsewhere. So NIST, which is the National Institute for Standards, basically, so it operates these time services. Some of them are being actually stopped now because GPS exists. But essentially, these are radio stations with very high power, operating in the shortwave band. I don't know if any of you have used shortwave, but this is what is used for long distance communications. So what happens out here is that this is a radio signal on which is modulated are digital bits, which are basically saying time is this, time is this. They keep repeating that. So essentially, there is an atomic clock. NIST is the one who maintains the standard time in this country. On top of a very stable carrier frequency, they basically have binary coded decimal time information. So it transmits year, day of year, hour, minute, second. So basically 31 bits and then a whole bunch of other information, and that's transmitted. So if all you have to do is to make a cheap radio receiver, and then you get the time information. Now the trick out here is that, or the issue out here is that you still have a delay, right? I mean, for example, the transmitter in this case is in Colorado. So by the time you get the signal, certain number of milliseconds would have passed. Coast to coast, this country is around 30 milliseconds. So let's say Colorado to California, maybe, I don't know, 10 milliseconds, let's say. So so you do have that error. So this is equivalent to saying the reference time is saying time is this, but by the time the signal is coming to you, there is a offset which has crept in, and without knowing where you are relative to that sender, there is no way to compensate for it because you are just receiving that signal. So, but if you remove the path delay somehow, let's say you knew the location, then you can get the uncertainty, which is extremely good, 100 microsecond kind of stuff. So essentially that's the jitter that you are seeing. There are many radio stations like this that exist, and this information is also available over phone lines. So essentially it gives you a cheap way of synchronizing, for all practical purposes, for most human users, sort of something which is pretty good, right? I mean, if your wall clock at home is millisecond accurate, then it's terrific. There are issues with this thing. Radio signal propagation does vary during the day with variety of environmental conditions. So you may go out of coverage and all, but again, the applications that these things are intended are one where the clock synchronizes once a day or once every few days. So it's not like you are continually riding on this clock, but it's a cheap way of doing things. The advantage here is that the frequencies are such that you can pick up the signal. This is 60 kilohertz, for example. So you can receive the signal deep inside buildings, even inside mines and stuff like that. So you can distribute things very easily. What this suggests is that there are many different ways I can carry time and frequency information. And around us, there are lots and lots of other sources which carry such information as well. So another example where there is essentially around us pervasive signal, and that is the AC signal. So in most countries, I think in all countries, the electricity is generated, the electrical networks are AC networks, either 50 hertz or 60 hertz, and they are kept very stable. They are kept very stable because if you have multiple generators on the same electrical grid and the frequencies are somewhat off, then the power flow can happen across generators and cause dynamics. So, so they're maintained with good long-term stability, and their website, if you just Google for like electrical grid frequency, you'll see many countries just publish it. There'll be a website and they'll have a needle and you can see what's happening to the grid frequency. So power companies try to keep the frequencies very stable, long-term stable, and so you can use that to make sure that your clock's frequency is stable enough. And so now what you can imagine doing is that if you, after you set the clock, you can use this signal to keep your clock in good control. So I mentioned in one of the earlier lectures that when you keep the frequency synchronized, it is really called a syntonization. So so what we have out here really is a syntonistor, because the AC signal only carries the frequency information. It doesn't carry the time information. So what I've shown out there is some hardware that from CMU, where essentially very low power, like microwatts, they could maintain very precise frequency, so that they can, once the clocks are synchronized, you can maintain good accuracy for quite some time. So what this suggests is that AC signal is one, but there are other signals around us also which have the same property, that they have somehow in them frequency related information. So another example is the television signal. Television in this country over the air is the NTSC signal, and that again is very precisely timed. The frequency is maintained very stably. So you could pick that one up. Cellular carriers obviously transmit time signal also. So there are a variety of sources that you can get frequencies, fairly stable frequency signals for free, and work off those. 802.11 systems also rely on time synchronization, just so as to deconflict channel access, something that I had discussed earlier as well. So one of the things that 802.11 in recent years supports are things like voice traffic and all, where you want to send packets on some periodic schedule. So as well as you also want to let nodes go to sleep. So what happens in 802.11 is that the base station essentially distributes time, and then all the clients sort of synchronize their clocks to the base station. So effectively, there's a special beacon packet which goes out, which says this is the time, and then the clients kind of hook up to it. This is essentially a local area version of that radio station thing that I talked about earlier, this one, right? Because it's a one-way time transfer. So, one entity is announcing time is this, and then other parties are listening and just setting the clock. In one-way time transfer, you will always have the issue that the offset, which is coming because of the distance, will never get compensated for, right? Because I have no way of knowing how delayed the signal is. So it's kind of like me saying time is 7 p.m., but if the signal takes 1 minute to reach you, then there will always be that irreducible 1 minute error that exists. But in 802.11, the distances are pretty small, so you get pretty good synchronization this particular way. So, so this one-way error is something that 802.11 suffers from. In AC signal, that's not an issue because we're only doing frequency. In this radio time service, that's an issue. In satellites, it's not an issue because we are estimating time directly via kind of an optimization approach. So ideally, what you would like to have is not be dependent upon not have this kind of distance error, right? We want to compensate for it somehow also. So kind of techniques which compensate for this error would somehow need to have a way of estimating what the travel time was. So to estimate that travel time, you will need some sort of bidirectional message exchange. You cannot do it from a single direction, because if all I have is one party sends a message to the other party, then you can insert an arbitrary amount of delay and there is just no way of knowing that. So if you want to estimate how much time transpires in between, what's the delay on this link, then I need a two-way message exchange, so that then I can estimate what the delay is. That's kind of the basic idea that ends up happening in systems where that delay is considerable. So NTP, which is the dominant synchronization protocol in the internet, is like that. So the idea behind NTP is that somewhere there's a set of sort of reference nodes in the internet whose clocks are synced to atomic clock, and then your computer deep down synchronizes with some other computer, and then there's a hierarchy of these things. Okay, if you are lucky, like for example here at UCLA, we can directly synchronize out here, because there are computer servers at UCLA which are kind of this top level servers. But otherwise, kind of the concept is we create this hierarchy somehow. And we'll see how the signaling protocol works, but what happens deep inside NTP? So NTP superficially sounds very simple, like I mean we are just talking to these servers, but deep down they have designed a system which is really meant to be very scalable. So just think about, like we have probably order of a few billion devices on the internet, and if you don't design the system properly, and if you synchronize too frequently, then the traffic on the internet, just because of the synchronization, will cause huge issues. So NTP is designed for very infrequent synchronization. So when a host comes up, it talks to NTP servers, but rarely. Okay, so because you want to distribute this traffic. So over the course of so eventually NTP becomes, if your host is up and running, you can get down to tens of millisecond accuracy. But if you just freshly powered up, that may not be the case. Also, because we rely on this hierarchy where level n synchronizes with level n minus 1 and so on and so forth, quality of servers is not necessarily the same. So some server may give you wrong time information, and therefore that error may creep in. So oftentimes what happens is that you synchronize with multiple servers and then find outliers, discard them, and work with those. To minimize the frequency with which you are synchronizing, so what NTP does is it models the drift of the clock. So the idea is that instead of simply, we are not simply doing the following, that I ask you what time it is, set my clock, and then run free. And then maybe a day later, again, I ask you what time it is, and again set my clock. Instead, what we do is, based upon these measurements, we develop a model of how my clock is drifting. Okay, so we fit a Kalman filter or something along those lines, so that we can predict how my clock is drifting, so that in between synchronization, we can still compensate for the clock. So it takes some time to get enough measurements to learn how my local crystal oscillator is behaving. So there is a lot of stuff going on in NTP, and these are pretty complicated pieces of code, but intuitively you are modeling the clock so that in between synchronization events you can still compensate, and you also minimize the need for synchronization, the need for frequent synchronization. So almost every major operating system provides what are called as NTP daemons, which is basically a piece of software running on your computer, which talks to NTP servers. You can configure which NTP server is talking to, and then it adjusts the system clock. So for example, Linux provides a whole API by which processes which have the right authority can adjust the system clock. In essence, when we are saying we adjust the system clock, what we are really doing is we are updating a calibration matrix. Okay, so there is a real hardware counter which is being incremented whenever the timer interrupt comes, but then before its time is made visible to the applications, it's basically multiplied by a matrix, and you are really to do a coordinate transformation of sorts, and you basically whenever you are synchronizing with, whenever NTP daemon is synchronizing with the NTP server, it's basically updating the parameters of that matrix. So so if you have NTP daemon running, you can get pretty good accuracies. Now there are some interesting there is nothing which says that you have to use the NTP daemon. Your own application can also directly talk to an NTP server and implement equivalent functionality. So if, let's say, for example, your computer doesn't have the NTP daemon, then you can roll in your own code which does that. So so that's kind of the idea. NTP server itself also is needed. So if, let's say, for example, you have a whole bunch of IoT devices in a local area network and you want to have them time synced, then you can run your own NTP server, perhaps even with a cheap sort of a GPS receiver, for example, with the PPS signal. So you can buy now little boards for Raspberry Pi, for example, which makes a Raspberry Pi into a NTP server, and you put one of them in your home network, and now you have good quality time available. Now, for all of this thing to work, the challenge out here is the following. So remember, I was saying that if the NTP servers were to simply say time is this and the time propagates, then the delay through the internet will kick in. And the delay through internet can be a lot, but more importantly, it can vary a lot. So you could be supremely unlucky, and the packet coming to you may be subjected to milliseconds or tens of milliseconds of delay. So what happens typically is, we'll see later, that there is a bidirectional message exchange that we do so that we take care of the delay through the path that would otherwise happen. So NTP, there are entire books on NTP, so I'm kind of obviously rushing through it in just one or two slides. Main thing is it's industry standard, it's available all over, and it achieves reasonably stable, let's say, order of 10 millisecond accuracy type thing. I wrote secure, which is not quite true. So like many other protocols on the internet, NTP was designed in an era which was far more innocent than is now the case. So there are lots and lots of security issues that actually do exist in NTP, and they are being kind of fixed in recent years. Cons, designed for millisecond level accuracy only, even if you are on a LAN, where otherwise delays are sort of low, even then you are still in or single digit millisecond at best. It's designed for constant operation in background at low rates, so it's really optimized for lots of machines being synchronized on a network. So for example, NTP may take hours to reach sort of a stable thing, so its space, its applicability space is kind of different, but over long run, so if you see out here, this is where NTP is. Over long run, it can have very good characteristics. So if you are just interested in maintaining a good clock over long run, then NTP does pretty well, but you're kind of limited to this millisecond range. Okay, so now what's let's jump to kind of IoT type system. So we saw some of the application needs that they have in one of the earlier slides. The main thing though is that in these systems, a few things differ. Firstly, in many cases, the accuracy requirements are much tighter. So by that, what I mean is that we are often interested in sub-microsecond type accuracies. Like for example, let's say there are a bunch of sensors and which are on the lookout for acoustic events, and then when they hear the acoustic event, they're going to localize them. So now you are suddenly into accuracies which are kind of pretty tight. One group has been doing this project where you want to hear where the car is coming from, okay, from to microphones. And again, if you kind of work out that what would be the time, let's say the car is 100 meters away, what would be the difference between the arrival of the audio waveform on two microphones on your body, it's going to be pretty tiny, and you're going to try to measure that very precisely. Our ears and brains are pretty good at it if you think about it, right? I mean, we are pretty good at identifying which direction a sound source is. So our brain obviously has developed the necessary logic somehow in our brain. So time sync applications which require tight time sync can easily get into sub-millisecond, sub-microsecond, or even nanosecond. Aircraft speed type stuff and all gets into tens of nanosecond, for example. Also, the other challenge is that oftentimes we want very rapid synchronization, and we also may want it synchronization at very low energy cost. So starting around early 2000s, when IoT / sensor networks and all started coming into play, a lot of work has happened in synchronization protocols which are specifically for this domain. So NTP doesn't quite cut it. Meanwhile, even for mainstream internet type applications, also people realize that they need much better time synchronization. So in particular, I mentioned finance industry, for example. There again, people talk about now nanosecond type time synchronization at a planetary scale. Now, the flippant answer to a lot of these things is for those applications maybe have GPS everywhere. And indeed, if you can, then you should. But we talked about the limitations of GPS in many cases. So what we are going to talk about now are how kind of more at a under the hood level, how these different systems work, and kind of there's a whole space of them. So our basic problem is I have some network, could be the internet, could be a local area network, and have some nodes with local clocks, and we want to synchronize them. So, and by synchronization, we basically mean we want them to report time, which is within a few, within a small delta of each other. So essentially the idea is if an application running on node 1 were to ask its local clock what time it is, and if an application at node 2 at the same time were to ask, they will get the same time. So that's the property we want to achieve. So, so how does it work? So basically what we have is a problem of calibration. So if you think of your local clock as a sensor of time, right, it's basically measuring passage of time. So what we are really trying to do is we're trying to calibrate it with respect to some agreed upon standard, right? Some agreed upon reference. Maybe when the global scale is the atomic clocks, for example. But our local clocks are imperfect. So what are the imperfections there? Firstly, their initial offset, their starting value. So different nodes in the world are going to start at different times. So when they start, let's say the counter starts at 0. So the 0 of one local clock and a 0 of another local clock is always going to have some offset in it, because it's basically impossible to get everything to start at the same time. So there is an initial offset, and which we just call as C0. Then there is a drift, which we spent considerable time on earlier, but essentially the idea is that the frequency is erroneous and frequency is changing over time. So if you think of the clock, local clock, as C of t, so in the sense that t is your true time, the true universe time or system time. C of t is what your local clock says the time is. Then the rate at which your local clock is advancing with respect to true time, that itself is varying. Yeah, that's really the frequency. So that omega of t, which is the frequency of your local clock, is something which is time varying, which is why they've written it as omega of t. And the clock, the time reported by your local clock is now going to be the initial offset C0 plus from 0, essentially from startup to now, the integral of the frequency of your local clock, right? So this frequency is time varying. So integral of the frequency since we started plus our starting clock value. So what we really are seeking to do in some senses is we need to be able to compute this integral, and we need to know this C0 somehow conceptually. Now, so this is like any other sensor calibration problem, which is my true value is the t, and I want to, but what I'm measuring is whatever my sensor measures, and then I want to derive the true value of time from that. So there are, how we approach this problem and how different systems approach it, in part depends upon what we want out of our timing system. So this leads to another issue, which is what kind of time service we want to provide to the application. So one perhaps the most common way of thinking about time is that I want a service which tells me the global time. So my system has a local time. It has this C of t or Ci of t for the ith node. And what I want is some function, some piece of software which converts the Ci of t to t. So that's what NTP does. So NTP basically learns the necessary parameters so that then you can read the local counter and then obtain from it what the global time value UTC is. But there are other type of things that we often need. So for example, map to local time. I might say when it is 7 p.m. UTC, what would my local counter say? And that would basically take into account the drifts and all. Or we can say when it is 7 p.m. at node A, what time it is at node B. So that, for example, may happen if some sensor sends me saying, here is a measurement and I took it at time t according to its local clock. When I get that reading, I want to translate that into my local clock so that I can maybe combine it with my readings. So there are many different ways you can think about the time problem, but the most common one is I just want the global time. So the common way we do this synchronization is the following: that periodically we measure, we basically do some sort of handshake so that we measure that at the current point in time, what is the offset between my clock and the other node's clock. So essentially at certain intervals, we will consult our neighbors, any network neighbor, and we are going to ask them what is the offset, and we are going to call it OIJ. So think of that as kind of like a measurement we are making. We are saying at this present time, what is the estimated offset between node J's clock and node I's clock. Okay, we'll see how one can do that. Remember, we cannot do it by simply saying, we cannot do it very nicely by simply saying one node sends the reading, another node receives it, because then we have the distance effect, okay, the propagation delay. So we have to do somewhat better than that. But let's assume that every so often, at different time instants, I'm able to do this offset measurement. So we have nodes with these clocks, and right now we did a measurement. Let's say a second later we do another measurement, a second later we do another measurement. How do you think these measurements will change? So let's say every second, let's say I have a clock, let's say Vivek has a clock, and every second we do an offset measurement. By that what I mean is, so our clocks are free running according to a local oscillator. At every second we do a estimation of what the offset between our two clocks is, right? So firstly, will this offset be the same? No, right? Because the clocks are drifting. Okay, so from the offsets itself. So now every second we are measuring the offset. So from the offsets, what can we know about the clocks?
We can only know dw by dt.
We can do an estimate of dw by dt, right? Estimate of the relative drift between our clocks. So let's say my clock was a reference clock. Then by doing these offsets, we can measure the slope with which your clock was changing, right? So I can essentially fit a curve and get the drift of your clock or mutual drift of our clocks. So the idea then is that we do multiple measurements of these offsets, and then we use them for two purposes. We use them to measure the drift between our clocks, and we also use them to connect our clock. Now, this offset measurement is never going to be perfect because it itself is going to be an erroneous process. So let's say again, right now we did a message exchange, and we'll see what kind of message exchange makes sense. We are going to make a measurement, but like any measurement, it's going to have some error in it. And then a second later, we are going to do another measurement, and it will change partly because the clocks have drifted and partly because it's again a noisy measurement. So what is happening is that I'm making offset measurement between two drifting clocks, and these measurements themselves are noisy. So, and what we need to do from this, all of this noisy data, is that somehow we need to fit stuff to it to then estimate what time it is. So at an arbitrary point in time, we would like to say, what time is it right now at the other node? Okay, that's the question we want to answer. So this takes us back to underlying at the hardware level. What is happening is that if you think of the C of t as that counter in our clocking system, then the value in this counter, appropriately discretized, is the initial value of the counter plus the integral depending upon how the frequency changed over time. The software view of the clock, often what we do is we tend to simplify it. So this frequency changing over time is pretty complicated. But a very common thing done in software is we basically say over short time intervals, it's basically drifting linearly. Okay, so it's a reasonably good approximation that over short time intervals, the two clocks at two different nodes are going to drift apart at some rate alpha with some offset beta. You can use more complicated models, and some recent work has even attempted to use machine learning methods, deep neural networks, support vector machines and all. But most of the methods basically say, let's assume that over short time intervals, it is basically a linear clock offset. And with that, we will see that how we can build up that synchronization strategy. So stepping back a little bit here, so I mentioned this point during last lecture. Sometimes we are only interested in synchronizing the frequency. All we want to know is that the frequency of my clock is the same as the frequency of your clock, and this would mean that I can measure passage of time similarly as you do. Then there are times at which we want to synchronize time, and then finally synchronize phase. By synchronizing phase, I mean that not only the frequency, but their frequencies are aligned, and of course time is that we are literally reporting the same time. Okay, so how do we do these synchronizations? So to estimate that offset, which I mentioned earlier, and then from that to estimate the drift, we basically exchange timestamp messages. So, so there are a couple of ways we can do this. One is we send a message in which we carry the sender's timestamp, and then the receiver timestamps the message also. Explicitly, so like at some time I'm going to send a message from my node to the neighboring node, and I'll say I sent the message at time t1 according to my clock, and we'll see how we can play into it. There's an alternative strategy where we agree a priori that I'm going to send you a message every second according to my clock, okay, in which case you can say it's implicitly timestamped. Then the second aspect of the strategy is, am I doing unidirectional messaging or bidirectional? So we saw unidirectional messaging in the radio station based approach, and essentially the idea is that let's say every second I send you a message, so you know that I'm sending the message every second. You are going to be receiving that message at some intervals which will not necessarily be a second apart because your clocks our clocks are drifting, but we can use that to estimate the relative frequency, or what is called a slew rate out there. But if we are willing to do two-way message exchange, then we can see that we can get the offset also. So essentially in the message exchange, a bidirectional message exchange, we will measure both how our clocks are drifting, and we will also get the offset. So let's see how it works out. So the basic idea is the following. Let's say I have two nodes. This node A sends a message, and it sends the message at time t1 according to A's clock. So the subscript means this timestamp is related to A's clock. So a message is sent from node A at time t1 according to A's clock, and that message is received at node B at time t2 according to B's clock. So if you go under the hood, then T2B will be equal to T1A plus the delay that will take place through the network because of speed of light and any switching delays, plus the offset from A to B, because this is how we translate A's clock to B's clock. So T1A says this is when the message was sent by A. Delay is when, if B's clock was synchronized, then it would have received the message at T1A plus delay A to B. But since the two clocks are offset, so right now whatever is offset between A and B, I have to add that. And the challenge in this case is the following: I don't know the delay. If I know the delay, then with this single message exchange and knowing T2B and T1A, I can measure the offset. Okay, but I don't know the delay. Now, even let's say the delay was 0. T2B is T1A plus offset AB. Do you think this measurement will be perfect? If no, well, rhetorically I'm asking because it's not going to be perfect. Question is, what sources of errors do you think will exist in this equation? So let's say delay was 0, and I say offset AB is equal to T2B minus T1A. So what sources of errors are going to be present in that measurement? Anyone? Any thoughts?
So once it's calculated, it's forever the same.
No, sorry. Okay, so sending the message, A jotted down T1A, B jotted down T2B. They exchange that information. So if delay was 0 or delay was known, then offset AB is equal to T2B minus T1A minus either 0 delay or known delay. So my question is, what sources of error do you think would exist in this measurement? Because if this measurement was perfect, then I have the synchronized clocks. But so to estimate offset, what am I measuring? I'm measuring these two timestamps, right? When I'm sending it out and when I'm receiving it. And if you think about it, these measurements are very hard to do precisely also. Let's say you are writing a piece of software where you have to measure precisely when the packet arrived or precisely when the packet was sent, right? At the very least, you will have an error corresponding to the frequency of your clock, right? That's a quantization error. If I can only measure in 1 microsecond steps, then T2B and T1A are going to be normalized to or quantized to 1 microsecond. So I will certainly have that error, but then also my the software stack and all is also going to put limitations on this thing. So these T2B and T1A are not are noisy measurement themselves, and therefore offset is noisy measurement. But worse, delay is not zero. Delay is not known. So so that introduces another complication as well. So, but let's say if this is the only type of message exchange we have, that is, A sends a message to B, and either T1, and it sends a sequence of messages. It sends one message and then follows up with another message. So I have a series of T1A and I have a series of corresponding T2B. Then I can measure a series of offsets. And from that series of offsets, I can compute how B's offset was changing relative to A over time, and therefore I can get B's frequency relative to A's frequency. So I can measure measure these things just from one-way communication. So it's very easy to estimate drift in time just from one-party broadcasting. So it could be some central entity. A could be a server, and it just sends out these messages. And if delay was 0 or fixed, then I can compute the drift in the clock. But the delays are variable, unfortunately, so that introduces complications even in that. So if you look at sort of what we are really measuring is that I may start out at some point in time, and then over time, kind of different nodes, their clocks will keep drifting apart because of the changing clocks. Okay, so back out here. So from this equation alone, I cannot measure the delay. So let's think about the following problem. Let's say I have two nodes and I want to measure the delay between them. Let's say there are two computers on the internet, and I want to measure how much time it takes for a packet to go from one node to another node. How would you do that?
To ping.
No. So my question I'm asking is, how does ping work? Right? You're right. Okay. So so describe to me, how would, let's say you have a node, I have a node. How would you measure the delay?
You have to send a message and then they.
Could someone else attempt to answer? Come on, guys. Someone from the side.
Use system lock.
Huh?
Use the system lock.
You use what?
System lock. Firstly, synchronize the clock of the two bars.
Okay, good. So if my clocks were synchronized, then I have an easy solution, right? If everyone in the internet had GPS, then I can send the message to you. You can tell me when you received it. I know when I sent it. We can subtract and we'll have the answer, right? Okay, but we don't have that, right? We don't have synchronized clock. So now what can we do? So let's say there's no synchronization. You have a free running clock. I have a free running clock. Okay, and essentially every time I send a message, it will look something like this, right? I can timestamp it. You will receive it. You can timestamp it, and this equation will hold true. Right? Your received timestamp is going to be equal to my timestamp, sending timestamp, plus the delay that it took for the packet to go to you, plus the offset that exists between our clocks. Can you think of a way that by making some additional measurements, I can compute the delay? So intuitively, again, so let's ignore this equation. How would you do it? Let's say you're trying to measure the network delay between two nodes.
Round trip time.
Okay, round trip time. So what would I do? I send a packet, you bounce it back, I get it. That's the round trip delay. I divide it by 2. What are the sources of error? Someone on the side? You want to take a shot?
Not sure.
Okay. So again, I sent a message from node A, sends a message to B, B bounces it back. A measures the time gap between sending and arrival. So that's a round trip delay. And we say an estimate of the delay is that round trip time divided by 2. And the question is, what are the sources of error in that?
The two paths may not have the same delay.
Okay, excellent. And which is why, if you notice, I put A to B because B to A may be different. So the asymmetry of the path may enter into picture. So that's one. Can you think of some other factor?
The clock is too bad, it will drift.
Okay, good point. Clock may drift, particularly if this exchange is taking too long. So the clock may drift. What else? B may not be able to bounce back immediately, right? So some indeterminate time may transpire, right? So we also have to make sure that we properly account for the time, all these times, right? The time it takes to go to reach B, the time it takes for B to bounce it back, and then the actual return time. But what it shows is that with some assumptions and engineering, we can now hopefully solve for offset also, right? I mean, this equation didn't give us the offset. It gave us the rate of change in the offset. But what we now do is, I'm going to jump ahead a few slides. What I can do is the following. I can first send a packet from A to B. So I have the timestamp on the sending side, timestamp on the receiving side, and this equation will hold true, right? T to B is equal to T1A plus delay A to B plus offset A to B. And this is the same as before. And then what B can do is, it can send a message back from B to A. It will note down when it's sending the message, when it is receiving the message. And by the way, on this message sending backward, it will also put T to B. So this equation will look like T4A is T3B plus delay from B to A and offset A to B. Minus offset A to B. And you solve this thing algebraically with the assumption that the two delays are the same, that is, my path is symmetric. Then essentially I can solve for the offset and the delay because I have two unknowns, the offset and the delay. What it shows is that really I have three variables here, right? Delay from A to B, delay from B to A, and the offset. But try as I might, I cannot, if you add another equation, again, it's not going to help me because every time I'm adding an equation, I'm basically adding a new variable. So the problem is that it's without synchronized clocks, without clocks which are already synchronized, you cannot measure one directional path delay. What you can measure is round trip delay, delay A to B plus delay B to A, or equivalently assume symmetry. So because if I have a priori synchronized clocks, then I know that means I know the offset. So then I'm back to two variables. But otherwise, what all synchronization protocols of this nature do is they do this type of bidirectional exchange, and each time they do this exchange, they're measuring two things. They're estimating two things. They're estimating the offset, which remember changes with time. So next time I do this exchange, offset would have changed. And also they are assuming that the delay from A to B and the delay from B to A are the same, at least over the course of this exchange. Do you think that is that assumption reasonable? Is it reasonable to assume that delay from computer A to computer B is the same as B to A? If not, why not? So again, I wouldn't be asking if the answer was yes, it's reasonable. It's not reasonable. So any sense on so let's take Ethernet, LAN. Do you think that delay would on an average be symmetric? No? Why not?
Traffic shipping and all that.
No.
So sometimes the packets take different paths. So,
Well, it's just an Ethernet, so there's no path. Right. Over the internet, there is no guarantee of the path it will take. So it could be my packet from here A to B can take a totally different path from B to A. So one of the issues is, I mean, if you look at the technologies that we often get to use, cellular and these kind of things, they're or cable modem, they're highly asymmetric. How many of you have cable modems? No one? You guys don't work from home? You have it? That's it? Two people? Okay. So what do you guys have? I was curious. Huh?
Wi-Fi. That's cable.
No, because you're living in the university housing. No. But then how is your Wi-Fi connected to the broader
it's
internet?
Cable modem.
Yeah.
Huh? Cable modem, right? Okay. So what kind of cable modem plan do you have? Anyone with a cable modem want to, like, what plan do you have? The data rates.
About 1 GB.
Well, they usually have like a different download and upload.
Upload, exactly. That's what I'm arriving at. So, do you know what those numbers are for your plan? Okay, next time.
160.
Yeah. Huh?
About 100 download and 60 upload or something.
60 upload? Wow, your cable modem company is pretty good. So the upload numbers tend to be much smaller. Okay, the reason they are much smaller is because on the upload, it's a kind of a harder problem you're dealing with, right? Multiple parties are competing to send to a single entity, right? So there is less control. So, like, for example, my plan is at my home is a gigabit plan, downlink 900 some megabit per second downlink, and uplink is 30. Okay, highly asymmetric, but more typical plans, the uplink might be just 10 or 15 or something like that, or even smaller. Same thing is true for cellular. If you look at the delays that are encountered uplink, they are much higher, and the rates are, delays are much higher, rates are much lower. So it's very common in a lot of technologies that you have this kind of asymmetry. So this assumption, while true in some settings, like if we were on a LAN and both parties were symmetric, like two computers in my lab, we'll probably see reasonably symmetric delays to each other, but in a lot of settings that's not the case. And then also, as someone mentioned earlier, different paths to the internet is another challenge, right? The routing in the internet need not be stable either. It changes from moment to moment. It could also be that you're sending the packet and it goes to an intermediate switch, and then it's unlucky enough that it arrives when there were some other packets there. So response is queuing delay is more. So if you plot delay between 2 points, then you would see that it's highly variable because of cross traffic, other traffic in the internet. So these delays are noisy, as in they vary over time, and they are not symmetric. So long story short, therefore, these two equations that I have to solve for offset and delay, they're kind of noisy measurement. You can think of them as every time I do this message exchange, I'm making a measurement, but I'm making a noisy measurement. Okay, as a noisy measurement of offset, which is what we are interested in, and the reason it's noisy is for all those reasons that we kind of talked about. Okay, so back out here. So what's happening now is the following. I have two nodes, A and B, and every so often I'm making an offset measurement between them by doing this exchange, right? So if we either we knew the delay, or we do that bidirectional exchange, but what we have is the offset measurement. Except what is happening is that the two clocks are drifting over time, and as I mentioned earlier, we can assume that for short time intervals, the drift is linear. So you can say ideally they are drifting in a linear manner over a short time interval. But our measurements are noisy. So what we have is I will measure the offset, so we expect them to be scattered around this line. Right? So each blue point represents a measurement we took of the offset, except this is a noisy measurement. So looking at this, a problem that you've probably encountered all the way from high school, which is linear regression. So we just fit it in, and now we have parameters of this line, best fit line, and using that, I'm getting two things. I'm getting how the two clocks are relatively drifting, and I can also use this best fit line to project out. So like, for example, let's say I had done the first three measurement, and before I have the next fourth measurement in between, I can basically extrapolate using this linear regressor to estimate what the time is. So instead of saying, so the main thing out here is that instead of saying the offset is the same as what I last measured, we are actually always estimating the offset using a history of measurements. One can show that going quadratic can do somewhat better. After that, you really don't gain much, because if you so usually kind of you fit over a short time interval and just linear. This is the place where some recent work has also begun to use more machine learning type models to do this prediction. There's a paper out of Stanford and Google last year called Huygens, and they showed that within data centers, like servers in a data center, they could do nanosecond type synchronization using some ML methods laid on top of this. So the problem they were solving is that if you have different virtual machines running on their data center, you want them to be very tightly synchronized if they're doing some time critical task. So basically what the strategy then boils down to is that we use either this kind of exchange where we estimate offset and delay both, or we just use the one directional exchange where we say I know the delay and then I can measure the offset. And in either case, then what we do is we fit a line to our measurements, and that lets us compute the time at any given point in time, or line or some other low order polynomial. Okay, so this gives us so the problem in a way, this is the reason I called it clock calibration, is because this is pretty much like what we do with any sensor calibration. We make measurements and then we fit a curve to it to estimate the parameters. In this case, the parameters are for the line that we are fitting. Okay, so what is beneficial at this point also is try to understand what are other sources of error that creep in, right? So we already talked about the delays. The path delay may be different in the two direction. They may be changing, clock may be drifting while we are doing all this exchange, but what other things are there? So to understand that, you can go into the hardware level a little bit. So if you look at what happens at the hardware level, at some point the software says send this packet. So the packet is then handed over to the radio hardware and the protocol stack, and then the radio hardware is going to wait to acquire the channel. It has to compete for the channel and access the channel, and then the actual packet transmission takes place. So the first bit of the packet goes out, or first byte goes out in the beginning, and then after some propagation delay, it is received at the other end. And then finally, when the packet is received, then it's handed over to the receive side of the protocol, which then raises an interrupt, tells the application, hey, there is a packet for you. So another way of sort of kind of now looking at this is that if I look at the end-to-end delay in the system, then I have some software delay associated with the operating system and all to send the message, that initial thing, send the message, the API calls, system calls, whatnot. Access is what is done by the medium access control protocol. This is the one which arbitrates the channel. And this is where you can have potentially huge delays because it's like a queue. Your packet is waiting, and there are two kind of delays. One is right at the sender, there may be some packet sitting in front, which may need to go out first. So you have that challenge. And the other one is there may be other nodes on the same channel which are trying to send stuff. So depending on how much load it is, this MAC delay introduced during this access phase can be quite long. Then the actual transmission takes place. This is the low-level radio circuitry, which modulates the bits and sends it out. So again, there will be some delay in that. Then there is the propagation. This is the speed of light. And then the receive side, again, kind of the radio receive electronics, and then again the software delays. So we have all these delays which are present. And if we were to do things naively, which is we timestamp in our software out here, and just like we're sending the packet and we note down the time, and when we receive the packet, we note down the time, then our timestamps are going to be highly noisy because we have all this other stuff going on. In particular, MAC delays are, as I mentioned, are highly variable. They are very traffic dependent, but also when you go through the operating system, the interrupt delays and all can kick in. So the packet may have arrived at some point in time, but because of scheduling and interrupt delays, by the time my application sees it, some variable amount of time may have passed. So doing this thing, if your whole thing is very deterministic, then I could get away with just application level timestamping. But if it's not the case, then things can be highly variable. So let's say you were designing this system. Where would you timestamp if your goal is accuracy? Where would the transmitter timestamp and where would the receiver timestamp if you want really super accurate time?
Transmitter should be at the TX.
Hmm?
Yeah.
Yeah, so you would actually do as the bits are going out over the antenna and as they're arriving over the antenna, right? You want to do it as close to the proper actual channel as possible. Now that's pretty hard because radios are not designed for timestamping. But there are, Ethernet cards you can buy with that low-level timestamping, but most of the time the hardware is not. One convenient place to timestamp is after the MAC layer, because MAC layer is where all the variation is happening. But again, the software has to support it. Again, the radios may not provide control over it. So all of these things introduce issues. So, and if you know that things are deterministic, what you can do is you can calibrate. You can take your devices and measure in a lab setting what the delays are, like how much delay in the access, how much delay in transmission and reception, characterize them, kind of do some plots and all and get some data and work with those. But otherwise, your best bet is to timestamp at a low level, okay? Ideally, just on either side of propagation, but as I said, that's usually very hard to do, so in the TX and RX layer. So if you were to conduct experiments and plot these delays between transmitter and receiver, with these, even with these low-level timestamping, okay, so this is these are some data points from my lab, and what you see out here is, so what we have is a transmitter, one node transmitter, and there are two receivers, and at a very low level, we timestamped the same. So transmitter is sending out a packet, it's being received by two receivers, so it's going out at the same time from the transmitter, same packet, and then we look at a particular byte in the packet and we timestamp it, and now you see this kind of distribution, okay? So what you're seeing is that between when the transmitter sent it out and when RX1 received it, so we basically take the signal from the hardware and then feed it to a instrument and we plot it, and likewise we did it for RX2. And then finally, we also did the comparison between RX1 and RX2, okay? So you see a distribution out here. And the reason behind this distribution is that even the delays out here, Tx and Rx, they're not entirely deterministic, because the packet modulation demodulation algorithms, they themselves have some data dependence, some variation, also clock quantization, time quantization issues kick in and all. So so you end up kind of seeing that. But nevertheless, what you should note out here is, so I don't have the numbers on this one, but if you look down here, the mean is somewhere around 3.2 microsecond or something like that, but the spread is only around half a microsecond. So what this says is that the delay has a variation of around half a microsecond. The mean is whatever, 3 plus microsecond. But I can remove the mean, and then what I'm really left with is a spread, and that spread is the uncertainty in the measurement, right? Because I can always subtract away the mean with some further calibration, but I'm always going to have to deal with this uncertainty. In other words, with this radio, it would be very hard for us to synchronize better than half a microsecond or so, okay? Now, in a single measurement. Now, anytime you have a noisy sensor, what do we do to improve quality? Like if I give you a noisy sensor and you want to improve the reading, what do you do?
Oversample.
Huh?
Oversample.
Take multiple readings, right, and average them, right? I mean, if your noise is well behaved, you why do you call it oversample?
Like take more measurements.
That's not oversampling. Oversampling is a higher rate sampling, right?
Okay.
But yeah, take multiple samples and then you average them out. Okay, so that in effect is what we were doing out here, right? So we are taking multiple samples of a moving process, right? The clocks, we are taking multiple samples of the offset, except that the offset itself is changing, so we really had a regression problem out here. So so that's what these systems end up doing. So so we really have at our disposal two different types of measurement possibilities, right? I can do a one-way message exchange, in which case if I know the delay, then offset, we get the offset. If I don't know the delay, then by doing many of these measurements, I'm getting the rate of change of the offset. I'm getting the slope. And if I do this one, bidirectional exchange, so this is kind of another message probe that we have, then I get both offset and delay. So more generally, the way the synchronization protocols proceed is that once in a while they will do a complete bidirectional handshake. And then in between, they will just do unidirectional exchange to get the frequency estimate. So the idea is you measure the full offset at a slower rate, and then you keep your clock disciplined at a faster rate. You could do other kind of games here as well. One kind of work that a lot of people have done is that they just opportunistically make use of messages. So the idea is nodes in the network will just transmit a packet saying, I'm sending this message and time is t. And some nearby nodes are going to hear it and they will receive it and note down the timestamp. Over time, I get a graph in which for some of the edges, I have the measurements. And then we solve a graph optimization problem. So there are many ways you can approach these kind of problems. We're going to look at it next time around. But between a pair of nodes, this is what we basically do. So in effect, you have these packet exchanges are giving you a sensor to measure the offset and a noisy offset, and then you combine them together to get a good estimate of the actual offset, but the offset itself is changing. So so by developing a model, you can keep tab of what the time is. NTP does this kind of bidirectional exchange, but it surrounds it with a much more sophisticated model than simply that linear regression that I showed. So it does a lot more sophisticated stuff to keep track of how the clocks are drifting. So I'm going to stop out here and then pick this thing up on Monday. So, and meanwhile, if there are questions on the homework, let me know. One other thing I would like to emphasize is do participate, because if you don't engage in the class, then the class participation points are 0 for you. So, I mean, of course, in grade, those who participate will always have will leave better perception. So, do take part. Lectures are meant to ask questions as well, even if you are not understanding, because otherwise I have no way of knowing that going too fast or slow. So it's important, and there are lots of empty seats in the front. Perhaps sort of try to sit closer, and that way you can feel more engaged. But I think let's try to make it more of an interactive process. Anyway, see you guys on Monday. And my office hours on Friday as well.